This will be a short video clarifying the properties of the canonical measures on Carnot groups. In brief, working in exponential coordinates, we shall easily see that the Lebesgue measure is both left invariant and right invariant. And moreover, it is an Ahlfors regular measure. The Hausdorff dimension then can be easily computed and expressed in terms of the dimensions of the strata, of the stratification of the Carnot group. In particular, Carnot groups have integer Hausdorff dimension, and this dimension is greater than the topological dimension, unless the group is abelian, in which case they coincide. Let's see. Okay, so we start and we have G, a Carnot group, which, let's remember, this means that G is a simply connected Lie group with Lie algebra stratified as the sum of vector spaces such that V1 bracket Vj is equal to Vj plus 1, where we mean that Vs plus 1 is the zero vector space. Okay, now we are going to consider measures on Carnot groups. From the fact that this is a Lie group, then it's a general fact that it will admit measures that are left and right invariant. And because it's also an important Lie group, then the measures that exist, each left invariant measure is also right invariant. Okay, so what I wanted to say is that from the fact that G is an example of an important, and actually more generally you can consider locally compact groups, namely topological groups that are whose topology is locally compact, then you have existence and uniqueness of invariant measures. Okay, invariant measures. But now I will discuss directly this fact without the need of referring to these general results. Okay? So, but it's still good to know what are these facts. So that every locally compact group admits measure defined on the Borel sigma algebra. Let me call it Borel measure. Let's call the measure mu. That is finite on compact sets and left invariant. Where left invariant means if I take the measure of a set left translated by an element, this is the same measure of the set. This is for all A Borel and for all G element of the group. So an object like this is called left Haar measure. Okay. The second fact is that Haar measures are unique up to the multiplication of a constant. So, namely, every two, let me say non-zero. Okay, maybe one should do it in the definition. Otherwise, it's clear that the zero measure is a Borel measure, Carnot compact set, and that's invariant. Every two, so let's include that in the definition of Haar measure. Every two left are measured differ by a multiplicative factor, a constant. And of course, we have the same results for the right Hard measures. They exist and they are unique up to the multiplication of a constant. Another fact that's good to know, but we will not really use it, is that on nilpotent groups, every left hard measure is also a hard measure, so it's also right invariant, and for which we just call them hard measures. Okay. For Carnot groups, this will be much simpler to prove. Okay, it's good to know that something more general is true. Moreover, if we have a Carnot group, we might consider other measures. So, if G is the Carnot group, then in particular it comes with the Carnot-Karate-Odori matrix. So one can consider measures coming from the choice of the distance. And moreover, for every k, one can consider the kth dimensional Hausdorff measure. Let's call it HK. Of course, at most one of these measures is non-trivial because they might all be either 0 or they might be infinite on open set, on non-trivial open sets. So the question is, okay, for at most 1 HK is, for at most 1K, HK is non-zero and finite on compact sets. So a priori it is not clear that any of these measures is a hard measure. What is for sure clear is that they are left invariant because the hard measures are preserved by isometries. So one can ask, there exists some k for which HK is a hard measure? And what is this k? Okay, this is going to be true. There is going to be 1k, and now we will see which one should be. Okay, because we are in a Carnot group, remember we have dilations. Recall that we have dilations. We will denote it by delta lambda, and lambda was a real number. So, in terms of the stratification, we can write delta lambda as lambda identity of V1, lambda square identity on V2. So, using the decomposition, I'm writing the map as a composition, as a joint of maps. Okay. So this is how it's the block diagonal with respect to the stratification. This is the dilation. Okay. Now I'm going to define the following number Q to be the sum of the dimension of V1 plus twice the dimension of V2 plus and so on, plus S times the dimension of Vs. Okay, this is the definition of this number Q, and sometimes we might refer to this number as the homogeneous dimension. Okay? homogeneous dimension, which for now is just a name. Okay. So for this Q, what the important formula is that the determinant of delta lambda is going to be, you multiply lambda times lambda as many times as the dimension of V1, you multiply lambda square as the dimension as much as the dimension of V2, and so on. So this determinant is equal to lambda to the Q. Okay, so this is the important relation that Q has with respect to dilation. Okay. Okay. Now let's put ourselves now in exponential coordinates. So it's called phi from Rn to G are exponential coordinates. With respect to some basis, and we can think that also this basis is adapted to the stratification, and therefore now in Rn we can consider the n-dimensional Lebesgue measure. On Rn. Then the Lebesgue measure of a dilated set, since the dilation as determinant equal to lambda to the Q, this is equal to lambda to the Q, the measure of the set. This is for all A Borel. Okay, so this property will be important. Okay. Then let me recall something more. Because that for simply connected nilpotent Lie groups in exponential coordinates, this Lebesgue measure is both left and right invariant. One can prove this because the differentials are of the form 1 in the diagonal and something below, with respect to a basis that is adapted to the stratification. Maybe I will recall this again. Okay, but so we expected so the Lebesgue measure in coordinates, the Lebesgue measure is a hard measure. Now what we want to check is that this measure, Lebesgue measure Ln, is equal to the HQ, maybe up to the multiplication of a constant for some C non-zero and final. So this is what I want to do. So really the Lebesgue measure is the Q-dimensional Hausdorff measure. Okay. So I'm going to prove it as a proposition. I'm going to prove something more. Okay. So let's say that we have a Carnot group with the usual stratification, and we define this Q, which is the sum of J dimension of Vj. Now, first thing, the Lebesgue measure and in exponential coordinates is the a Hausdorff two-dimensional measure up to the multiplication of a constant, up to a multiplicative constant, to the Hausdorff dimension of G is equal to Q. 3, for every other hard measure, mu on G, we have that the measure on the ball radius r center P is equal to r to the Q, the measure of the ball centered at the identity element and radius 1. It's for all P in G, for all r greater than C. So this is even more than Ahlfors regularity, because these are really, this is an equality. Not only this is behaving as r to the Q up to a multiplicative factor. Really, from above and from below, it's really a constant factor. The ratio is constant. The measure of the uniform. So this is what I will convince you this. Okay, let's put that. One. Okay. Let me remind you why the Lebesgue measure is a half measure. So let's recall that every important the algebra admits what are called Marshall bases. Now, for Carnot groups, this is much simpler. For Carnot algebras, just take a basis adapted, any basis adapted to the stratification. With this basis, we consider exponential coordinates. So with respect to this basis, much of basis are enough. And now what you have is that you do the calculation that left and also right multiplications, translations, have differentials of the form 1 in the diagonal and something below. And this is because whenever you multiply, then because of the Becken-Campbell-Hausdorff formula, you can see that the elements is going to each coordinate when multiplied is going to have elements in higher order parts of the stratification. So once you prove this, then these maps in particular have determinant equal to 1. So these maps, they preserve these maps preserve the Lebesgue measure call it Ln. Therefore, Ln is a R measure because it's a Borel measure that is finite on convex. Okay, and now because of uniqueness of the R measure, we know that every other R measure there exists a constant such that mu is constant. But we don't need to use this for the Hausdorff measure. Now let's look at the Hausdorff measure. So now remember that since we have the determinant of the dilation equal lambda to the q, then what is the Lebesgue measure of an arbitrary ball? Now, by left invariance, we have this is the same of the Lebesgue measure of the ball centered at the identity. That is R, the identity of the group. Now, because of dilation, we can write this as the dilation by factor R of the ball with radius 1. Now, because of this property here, we have that this is the determinant of delta lambda, so it's lambda q, the Lebesgue measure of the ball of radius 1 at the identity. Okay? So where lambda is R. Okay, good. So what we have proved is that the Lebesgue measure in coordinate is Ahlfors Q regular measure, and one can prove for general metric spaces that this implies that also the Q-dimensional, so actually this constant in general, the Q-Hausdorff measure is Baliff's equivalent to the regular measure, and is Ahlfors Q regular. Okay, and in particular, being the Q-Hausdorff measure non-zero and not infinite, then the Hausdorff dimension of G is equal to Q. Okay, this is what I wanted to say about measures on Carnot groups. If you like the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on subRiemannian geometry, please subscribe to the channel clicking below. Bye.